as you can see, in steepest descent, from what we have learned previously, in steepest descent, we use what? We use the value of derivative, right? For our acceleration, for our direction, we use, here is first derivative, okay? There are another methods that use derivative such as steepest descent, conjugate gradient, or Fletcher. So now for today, we are going to proceed with Newton types, where still we are going to use the same algorithm, but the direction, the difference is for our direction. So the direction is important for us to accelerate the move towards the solution point. So the direction for Newton will use the second derivative Hessian, okay? Where in Newton, we are going to use inverse matrix of Hessian. Okay, so this is inverse matrix of Hessian. Just like steepest descent, okay, compared to steepest descent, we only use derivative, first derivative. Okay, so in Newton, we are going to calculate the Hessian matrix first, and then we need to evaluate the inverse of Hessian matrix. And the rest of the problem, the process is similar with the steepest. And then we have Quasi Newton. So in Quasi Newton, we have the FP and the FGS. Okay, these are all included in your syllabus, where in Quasi Newton, we use the approximate matrix Hessian. Okay, instead of using the Hessian according to the function, we approximate the matrix H. Okay, which is this matrix H is the approximation matrix to the Hessian inverse. Okay, so that we don't have to calculate the inverse Hessian for each iteration. So this is for this is the difference between Newton and Quasi Newton, where the Quasi Newton is the improvement method. Okay, in the improvement method from the Newton. All right. So as for today, we're going to discuss about Newton's method. Okay, just like here in steepest descent. Last week we have done with steepest descent. It used the information from gradient. Okay, we calculate the gradient. But Newton used quadratic estimation and used the minimum maximum f of the function as estimation. Okay, so use quadratic term in Taylor's expansion here means we use Hessian. Okay, so now we consider two cases, two-dimensional and also n-dimensional. So let's just discuss for n-dimensional, which cover all. Okay, so let's say we have a point of x1 and x2. All right, we have a point, then x plus epsilon here are the neighboring points. Okay, so let's say we start at x0. Initial point at x0. So fx1 can be calculated by fs plus epsilon transpose derivative fx. It's 1/2 epsilon transpose gx epsilon. So this is a quadratic estimation of fx, where this epsilon comes from the Hessian matrix. Later we can take a look at the example. Okay, where the delta fx is the gradient of f and gx. So gx here is del squared f del xj del xk as a Hessian matrix, this one. Right? The necessary condition to get the stationary point, where from this function we differentiate with respect to epsilon and then equal to 0. Okay, and then you can find the value of epsilon, where the epsilon is actually involved the Hessian matrix and also the derivative. Okay, and this is the iterative formula, where if you want to update the point, it is equals to x0, okay, the initial point minus with g inverse x times delta fx, where this G is Hessian. So G inverse Hessian matrix, then you inverse. Alright. Okay, this one. G inverse is the inverse of Hessian. So the general iteration of Newton's is given by this. Okay. So in 2 dimension, it's just the same one. You have a point, then you will have a neighboring point. So if you want to update it to x1, it involves the epsilon, then it can be expanded to this. So compared to the n-dimensional, we have here. And this one is obtained from the Taylor expansion here. So from here, you differentiate f with respect to epsilon equals to 0. Okay, and then we can have our values of epsilon in order to update the formula. Okay, so in the 2 dimension, we can just use the epsilon because this epsilon itself is the value of the Hessian inverse here. Sorry, here. Okay, so to make it general, we just can use this as our iterative formula. But there is an exception if f is not a quadratic. Okay, so usually this Newton used in quadratic because this iterative formula for Newton will help quadratic function to reach the solution point faster. Okay, but if f is not quadratic, sometimes Newton-Raphson diverge. So this method will diverge, okay, and perhaps converge to saddle point, where we cannot find our extremine. Then we introduce the scalar of lambda here in order to boost or to accelerate the iterative points. Okay, so usually this Newton used in quadratic, where our iterative formula will use this. Okay, but now if f is not quadratic, we introduce some scalar here, which is lambda, in order to accelerate the iterative. Is that clear? Understand, Anna? Okay, so now right, let's take a look at the advantage and disadvantage. Okay, so for Newton, it is such an advantage for quadratic function because we will get our optimum point for only one step. Okay, and if f is general function and the starting point is near to the optimum point, then also by Newton, it will converge much faster. Okay, so the advantages is for quadratic and also for a function which has the starting point near the optimal point. Okay, maybe this is your function, this is your optimum point, and maybe this is your starting point. This is x naught. Let's say this is your x naught, this is your solution point. If you start near to the optimum, then the process will be much faster. Okay, that is the advantage for using Newton. And of course, for quadratic, you will get the optimum point for only one step. So another disadvantages here, for each iteration, let's say this is the function is not quadratic. Okay, for each iteration, you need to calculate h and also inverse h for every iteration. So the development to minimum or maximum happens if G is a positive definite. Okay, minimum G should be positive definite. maximum, G should be negative definitely. So this method is not able to differentiate whether the point is maximum, minimum, or saddle point, because we always need to identify the characteristic of the Hessian matrix itself. Okay, so this is one of the disadvantages of Newton. Okay, now let's take a look at the example here. Let's use example 1. Okay, any question, guys? Everything's clear? Okay, so let's take a look at the algorithm. Okay, by using this example, we want to minimize the function starting at 5, 5. Okay, how can we use the method here? So now we start at I equals to 0, right? So at I equals to 0, we are going to have what? We are going to have x naught. Okay, so this method is quite simple compared to the previous method, but its advantage only on quadratic function. Okay, so now we want to minimize. Okay, here minimize this function. Let's start at 5, 5. So at I equals to 0, we have x naught. Okay, now your x naught is 5, 5. Okay, next, from here we need to calculate what is your fx naught. Okay, what is your derivative of fx, because it involves derivative here, and what is the derivative of fx naught. Okay, so at I equals to 0, at our initial step, we need to identify all of this. Okay, so your x naught is 5, 5. Your derivative is 4x1, 6x2. Okay, and then your fx naught, just substitute 5, 5 to the function. What should you get? 1 to 5, right? Okay, then derivative of fx naught, so substitute x naught here in your derivative function. So you should get 20 30. Okay, you have your derivative f, you have your f. Now find g. What is g? Remember, what is our g? G is our Hessian. So what is the Hessian matrix here? Okay, revision for your test. What is Hessian matrix? How can you obtain Hessian matrix here? You want?
Differentiate f with respect to x1 and then
X2, right?
x, sorry,
Differentiate derivative f again with respect to x1 and x2, right?
yes, okay.
So you will have what? A matrix of 2 by 2 because we have two variable, which is, what is the matrix here?
4006.
Okay, 4006. So I hope everyone has no problem with finding the Hessian matrix here. Okay, so now this is G. Then you can have what here? G inverse. So what is our G inverse here?
One over 400,106.
1 over
1 over 400,106.
1 over 001 over 6. This one, right? Which give you okay. Now you have your I. Calculate this one. Okay, so for lambda here is used only for non-quadratic. Remember, looking at the note. Okay, now we want to find our D. How can we find our D? Okay, how can we find our D? Why we have to find our D there? D is negative G inverse X times with derivative of F because we want to find our updating point, which is X1 equals to X0 plus D naught X. Okay, which is obtained by X1 equals to X0 minus G inverse X0 derivative of Fx. No, Okay, so we just use the value that you obtained here. X naught is 5, 5. Okay, inverse matrix here is 6 over 24, 0, 0, 4 over 24. Okay, and the derivative of fx naught is 20, which give you, so x1 is 0, 0. Okay, now check. When x1 is 0, 0, then fx1 is what? Fx1 is 0. What about our g? Okay, we have done with updating the point. Okay, and then determine the convergence. Xi plus 1 minus xi less than epsilon, or gi plus 1 less than epsilon. Okay, so we use g here, where g is what? Check g for derivative fx naught. So fx1, right? Which give you 0, 0. So now the modulus of gx1 is 0, which is less than epsilon. So usually epsilon is 0 0.05, 0 0.001, so on, right? Which is given. So what we can conclude here is the minimum value is fx equals to 0 with a minimum point x1, x2 equals to 0. So we can reach the solution point only at one step because this is a quadratic formula. All right. So zero, zero. Okay, so for quadratic formula, this is how we do the Newton's method. Okay, anyone has question for the basic Newton method here, where we don't involve the value of lambda there? Any question? Can you see this? Or is it too small? All right, any question? Everyone's clear for this method? Okay. Let's try another example, which is not quadratic. So this is quadratic, right? Okay, so now let's start this method for non-quadratic function. Okay. How can we do this? All right, so of course, first you need to identify your x naught. So x naught is 3. And then what? And then fx naught. What is fx naught here? Just substitute, which give you 7. And then differentiate f. Will give you, this is 2 variable, right? So we have here differentiate with respect to x1 and again differentiate with respect to x2. So this one becomes 3x1 squared minus 3 2x2 squared minus 2, where derivative of fx naught equals to 9. So this g here is actually, this one is derivative. Okay, the big one here is matrix, Hessian matrix. G here, Hessian. G here is derivative. Okay, so this is our step. So next, we need to identify what? What is our next step from here? What we want to find? Yes, our Hessian matrix. So what is your Hessian matrix here? The general form first, so that it's going to be easy for us to use the next iteration. So Gx is given by Hessian here. Just differentiate this with respect to x1 will give you 6x1 0, 0 and 2, right? Differentiate this with respect to x1, will give you 6x1. Differentiate this with respect to x2, will give you 2x2 here. Okay. That is your g. Okay. And then your g naught, gx naught, so substitute x naught here. Just has x1 there, so you just substitute 2 here. Then you have 12, 0, 0, 2. Okay. And g inverse at x naught equals to what? 1, 12 over 24, number 12, 0, 0, 1 over 2. Okay, anyone has problem until this point? So what we have done just now is collecting all the information used in this algorithm first. Okay, now this is non-quadratic, remember in our notes, where if we have non-quadratic function, sometimes Newton will diverge. Okay, so it is safe for us to use the modified formula. Okay, according to this algorithm, where it involves lambda here. Okay, it involves lambda here, where lambda is what? Okay, now we need to calculate lambda. So how can we calculate lambda? We have to have our xi first, x1 first. So now we want to update. So x1 is given by x naught, okay, plus lambda naught, d naught is minus, minus g inverse x naught times with delta f x naught. So x1 is given by 2, 3 minus lambda naught. G inverse is given 12, 0, 0, 2. Okay, this one is given by 9, 4. So from here, you will have 2 minus 9 over 12 lambda naught, 3 minus 2 lambda naught. So this is your x1. Okay, now how can we find lambda? So if you have your point x1, then you can find your fx1 by substituting the point here to the function. Okay, now your fx1 is given by, substitute here to f. 2 minus 9 over lambda, 9 over 12 lambda naught cube plus 3 minus 2 lambda naught squared minus 3 times 2 minus 9 over 12 lambda naught minus 2, 3 minus 2 lambda naught plus 2. Okay, so how can we find lambda? Refer to your notes. How can we find lambda? You can differentiate. Okay, in order to find our lambda, you can differentiate f with respect to lambda. Okay, and then equal to 0, right? So we can have our df d lambda equals to 0. So now f fx1 over d lambda naught equals to what? Okay, differentiate this with respect to lambda naught. Differentiate f here with respect to lambda naught. Will give you 9/4. Later you check again, okay? Okay, solving this will obtain you a quadratic formula of lambda. Okay, solving this will give you lambda naught equals to 1.1047. Lambda naught equals to 10.5496. Okay, so you need to test which lambda here will give the minimum function value. Okay, which lambda naught will give so just substitute x naught to fx1 here, sorry, lambda naught to fx1 here and identify which lambda. So lambda naught equals to 1.1047 will give the minimum function. Okay, as you can see, this is 1.1, this is 10.5. Of course, this one will give the more minimum function. Okay, then when you have your lambda, then you can have your x1. So x1 is 2 minus 9/12 lambda naught here. Now you just substitute the value of lambda naught that you obtained. Now you have your x1, which is 1.1715 and 0.7906. So this is your x1. Okay, and fx1 is given, is obtained. Okay, and then you check your g naught, gx1. Gx1 here is obtained by substitute x1 to your g. This is your g, right? Okay, and then you have g equals to 1.1172 minus 0.4188. So how you will obtain the modulus of g here? You just calculate the magnitude, which give you more than epsilon. Then you can proceed, continue the iteration. Again, repeat the step. Now you have your x1, then you can find your x2 by using the same step here. Okay, is that clear? This for this example, we are going to stop only at iteration 2. We just can proceed only at one iteration. Okay, the next iteration is iteration 2, then you will obtain your optimum point. So other than using the magnitude of G here, you can also find the stopping criteria by using the magnitude of xi plus 1 minus xi. Okay, so it means that you can find the magnitude of x1 minus x0. So either way, it can be used. Okay, x1 just x1 minus x0. X1 is x0 is, okay, so you can find the magnitude here. Okay, any question for the first iteration here in solving the non-quadratic by using Newton's method. So the difference between the quadratic here, we don't find the value of lambda. Okay, so in quadratic, we don't find the value of lambda, right? But for non-quadratic, we usually use this iterative formula and find the value of lambda first to accelerate the solution point, to accelerate the process of finding the solution point. Okay, any question? So this is iteration 1. I hope you can try with finding the next iteration. Is it too small? Can you see it? Anyone? Anyone has question? Anyone has problem? Can we have the final answer? All right, any question for this method? Okay, guys, anyone has question? So far, everything's clear? All right, so I hope you can try. This is for quadratic, this is for non-quadratic. So in your notes, there are another example of x1 to the power of 4 plus x2 to the power of 4. Use 2 steps of Newton method starting from 1, 1. So, okay. Can I just unshare the screen here? You still want to take a look? You? Okay, this one you can try. This is quadratic function. Okay, so for non-quadratic, it is better for you to use the iterative formula involve lambda here. Okay, so that is for Newton, right? So there is another way of solving the Newton where we can find the value of epsilon by differentiate the function with epsilon equals to 0. Same process, but it's a little bit of just an extra formula for you. So I'm going to stick with this algorithm only. Okay. So it it's not going to be confused. Okay. Now we have done with Newton's. Okay. And as just like I said earlier, we have done with steepest Newton. Steepest descent, where steepest descent is one of the gradient method. Okay, now we have Newton type method. So in our next method is a quasi Newton where we modify the Newton method. Okay, now it is called a quasi Newton where we use the approximate matrix of Hessian. Okay, there are two methods for this type of quasi Newton, the FP and the FTS. So what I'm going to do is for this DFP and BFGS, it is not quite different, but of course, still has different. Okay, it is not quite different compared to the Newton and steepest descent, just in terms of the direction. Okay, where it used the approximating matrices. So what I'm going to do here is, because this Wednesday is your test, right? So I'm going to provide you a video for the FP and the FGS, okay, which will replace the class time that is used for your test. All right, is that okay with you? Okay, so for this Wednesday, for this upcoming Wednesday, our class start at 11, right? Then let's just focus on your test on that day. So I'm going to give you a video of the FP and the FGS there. Okay, so our test one is on Wednesday. Let's start at 11:15. So the time is banyaknya masa. The time is 1 hour and 30 minutes. All right. So we get ready at 11. Then 11:15 we start. And we stop at 12:45. Okay. So ini macam biasalah for online test process. Alright. Okay, any question for today's lesson and for your upcoming test? Everything's clear? How many question? What's about now? I think it's 6. 6 questions involve basic calculus, start from basic calculus up to hook engine, and bear in mind not all methods used for calculation, otherwise you will have not enough time, right? So some methods only involve the calculation of iteration, not all. So don't worry if you have concern on such a long calculation, so on. Okay. Paper past year. Letak je lah paper past year. You boleh cari kan paper past year exam.